So we're continuing to build out the statistical techniques that we have available to us. We just finished talking about when you have three or more categories and an independent variable, and it's a between subject design, we're using independent measures ANOVA. Now we're going to add in what happens if it's the same people in each of those conditions. It's a within design, and we're going to look at the repeated measures ANOVA. And we're primarily going to be looking at how this differs from the independent measures ANOVA. So repeated or within subjects ANOVA, we're basically going to be talking about the slight differences in what we're actually looking at, how it's a slightly more powerful test because, once again, we're not having to account for individual differences. And we're also going to talk about the slight difference in the post hoc test that we'd use within this design. So when would we use it within subjects ANOVA? This test is used when comparing two or more, so again, three or more conditions or groups. If the number of available subjects is limited, in other words, if we are having a problem getting a large enough sample to have different people in each group. If we're trying to actually make over time comparisons, so for example, if our independent variable is time 1, time 2, and time 3, participants are either the same or matched on one or more covariates, so we're not using random assignment. It could be that there are different people in each group, but we've gone through a process to make sure that those groups are equivalent or they're the same people. And again, by doing this, we are reducing error prior to the actual statistical technique itself. We're using methodology to reduce the amount of error. The advantages and disadvantages, it does reduce individual difference and therefore increases power. In other words, the bottom of the equation is usually going to be smaller. The carryover effects are problematic. So again, we have to make sure that we are looking at something that we do not expect there to be carryover effects or time-related events. And there also are time-related threats to validity are definitely possible as well. So variance in the within subjects ANOVA does not measure individual differences since they do not exist between the group. So basically what we're looking at is the between when we're looking at a ANOVA that is between subjects, we have the between treatment difference, individual differences, and experimental error on the top, individual differences and experimental error on the bottom. When we're actually looking at this theoretically with a within subjects ANOVA, we have the between treatment difference still there, change difference, so we actually are looking at how they change from time to time. So we're actually stacking the deck, if you will, on the top of the equation, and then experimental error. And that change difference is also at the bottom of the equation. So instead of individual differences, we're actually including the fact that there are differences from group to group as we move forward. So when we're computing the within subjects ANOVA, the F ratio and MS ratio are very similar to the between subjects ANOVA. Again, theoretically, we're looking at between subjects at the top divided by degrees and mean squared between. It's basically the same equation. The bottom, however, is no longer sums of squares and degrees of error of within. It's sums of squares error divided by degrees of freedom error. So again, the terminology does change. We're no longer looking at the bottom of the equation as an MS within, we're mean squared. We're looking at the MS mean squared error. So between subjects, bottom of the equation is all unexplained variance, while with the within subjects, the bottom of the equation is just that error variance. That's all that we're actually putting into the equation. Because again, the group should be the same. So let's run through an example. We have 6 graduate students over time, and we're looking at coffee consumption increasing from baseline to summer. So our conditions is baseline coffee consumption before they enter the program, end of spring semester coffee consumption, and end of summer coffee consumption. So our hypothesis here is we're actually following the same 6 students over a period of time, looking to see if there is a change over that time. So again, we're going to formulate our null hypothesis and our alternative hypothesis and select our alpha. So our null hypothesis is there is no difference between the start, the spring, and the summer. And our alternative hypothesis is there's at least one difference between the various means as we move forward through time. Our alpha, again, we're going to set at 0.05, which is the standard. We're going to locate the critical region. We have 3 conditions and 6 people exposed to all conditions. So we're going to calculate our degrees of freedom. The degrees of freedom between is the number of groups minus 1. So we have 3 groups minus 1, that's 2. The degrees of freedom error is the number of groups minus 1 multiplied by the number of people minus 1. So in this case, we have 3 groups, so 3 minus 1 is 2, and we have 6 people. 6 minus 1 is 5. So our degrees of freedom for error is actually 10, 2 times 5. So again, our F critical value is 2, 2 and 10, and then we actually do the calculation. So again, we're going to check to see if it's significant. Look at the degrees of freedom chart. We're going to find that we need a 4.10 with the degrees of freedom 2/10. So that's what we're looking for. If we find that statistical significance, we're again going to do a 2-keys HSD. It is computed the same way for the within subjects as the between subjects, except that MS within is now replaced by MS error. Therefore, the equation is the same. We're still going to find the Q from a chart. We're going to plug in the MS error instead of MS within and divide by the small n. 2 can always be used for repeated measures since you always will have an equal sample size for each group. So the previous example, I said we're making the assumption that we have equal people in every group for the purpose of hand calculation. In the case of this particular test, we actually, the within subjects, we actually can always use this equation because we're always going to have the same number of people in each group. So again, we're going to get that Q value. In this case, it's 3 number of treatments divided by the degrees of freedom error, which is 10, 3.88. We're going to put 3.88, our MS error, 1.52, divided by our total number of participants, 6. It becomes 1.94. So again, at this point, our baseline, if we look at spring versus summer, baseline to spring, it's a negative 1.33. Which is smaller than the absolute value of 1.94. And if we look at baseline to summer, it's 2.83, which is greater than that 1.94. And if we look to spring to summer, again, 1.50, which is less than. So we only have one significant difference. Once we have the omnibus test, our HSD test is telling us that the actual difference is that coffee consumption does increase from baseline to summer. So a recap, the independent measures, ANOVA, we have access to a larger sample size, so it's okay to have different people in different groups. We may not be able to test and retest the same people, or we're worried about those effects. And we may be worried about time, maturation, and carryover effects. And again, theoretically, at the top of the equation, we have the between treatment, the individual differences, and experimental error. And at the bottom, we have individual differences and experimental error. The repeated measures ANOVA, the number of subjects is limited. That might be one of the reasons we're using this. We're trying to make overtime comparisons. In other words, our hypothesis includes maturation. We're trying to simply reduce error, make a more powerful design. And by reducing individual differences, it is easier to detect an effect because, again, all we're looking at is between treatment plus experimental error divided by experimental error. So we've gotten rid of individual differences in this equation. Again, carryover effects, especially if the same population is taking the same test over and over again, may be an issue as well. We'll talk a little bit more about this in the next set of slides.